Uh, Actually, Vishalakshi got the joining link.
Yes, ma'am. I got it.
Oh, you have joined. Okay,
Yes, ma'am, I have joined.
okay, okay. So I think it's 10 a.m. and the people will join slowly. They are joining also. Okay.
Yes, ma'am.
Yeah, yeah. So now officially he can start.
Huh. Okay, ma'am.
If you cannot do great things, do small things in a great way is a good saying. I welcome you all. Good morning, one and all. I welcome you all for the 5th day of International FDP. So today we have along with us Professor Vishalatchi S. It's my privilege to read her biodata. As a dedicated researcher in the field of 2D photonic biosensors, Vishalakshi brings a wealth of expertise and passion for advancing technology in healthcare diagnostics. With a PhD in 2D photonic crystal biosensor for healthcare applications, Vishalakshi S has emerged as a leading figure in the development of cutting-edge biosensing technologies. She began her academic journey with a strong foundation in engineering, earning a master's degree in VLSI design. Following this, she honed her teaching skills as assistant professor at RVC Tamil Nadu, where she inspired and mentored students in the field of electrons and communication. Driven by a desire to deliver deeper into research, Visalakshi embarked on a PhD journey while also gaining valuable experience as an intern. Her research focus on photonic crystal for solar cells reflects a commitment to exploring innovative solutions for renewable energy and sustainable technologies. Today, as a research scholar, she continues to push the boundaries of knowledge in 2D photonic biosensors with a vision to revolutionize healthcare diagnostics. Through their dedication, expertise, and innovative spirit, she is poised to make significant contributions to the field and create a positive impact on society. I welcome you, ma'am, and I
Thank
kindly request you to take over the session.
Yes, sir. Thank you so much for the introduction. Thank you, ma'am. Thank you, Preeta, ma'am. Thank you, sir. I want to thank HOD, ma'am, of EC Department too for this opportunity, and thank everyone. Thank God, and I will start my session now. Good morning, honored all present here. I'll show my screen, and we can start over by there.
And just I will stop here, Vishalakshi. People here separate message they are sending me. They are interested to learn the software.
Yes,
So
ma'am.
in group, you are also there, na? I have sent the, or else in chat box you can paste the software. So while you talk, they will install, and once they are ready, okay, they can learn. Okay.
Yes, ma'am. So before I will start, I will send the link, ma'am. Yes, ma'am.
Okay.
Sure. Yes, ma'am.
Uh, your photo is not coming, Vishalakshi?
Yes, ma'am. I just turned off the screen
Okay,
since I'm using my WhatsApp to paste the link.
okay, okay.
Huh.
So the participant today's session will be very useful because you are going to learn, okay, new software. So it will be helpful to all of you for your making the paper or anything. Okay.
The topic for today's session will be hands-on experience on 2D photonic crystal biosensor based on healthcare applications.
Uh, Ma'am, since it is not the link, it is an extension file. So can I send the extension file directly?
Yeah, in the WhatsApp you can send. You are also there in the WhatsApp, na?
Yes,
Where all
ma'am.
the
Our group
participants are
hidden.
there. So
Okay, okay.
participant, you will get it from your WhatsApp. Okay. So all of you see that. Because many talks we are listening. So listening talk from one side and one side it will go. But if Vishalakshi is very capable of giving the hands on, So it is a great opportunity for all of us to learn and understand.
Ma'am, I have sent the group Dr. Preeta Madam students. So in
Oh,
that
that
group,
group you have sent.
yes, ma'am.
Okay. Not you are not in FDP group.
No, ma'am, I'm not in FDP group.
Okay. I will
Yes.
send it. I will post it. Okay. I will post. You
Yes,
start.
ma'am. Yes, ma'am. Yes, ma'am.
Thank you.
Thank
Ma'am,
you.
sorry
Thank you,
for
ma'am.
interrupting. There are two files here. Opti FDTD setup and Opti rating. Both are needed.
I think no, sir. Opti grading is not needed. Opti FDTD is a today's session.
Okay. So once again, I'll post the Opti FDTD in the group so that
Yes.
Yes. Yes.
all participants can download.
Yes. Yes. I will send you Jairaj next also.
Ma'am,
You
I
can
have
post
that.
it.
I got that. I'm
Okay.
posting
Okay.
now. I'm yeah, I have put it.
Okay. Okay.
Yes,
You
ma'am.
can start,
All
Vishalatchi.
the
Yes,
participants kindly download this Opti FDTD setup file so that it will be useful for the hands-on session.
ma'am. Can you see my screen?
Yes, ma'am, it's visible.
Yes, sir. So I'll start here.
Ma'am, we can go for presentation. Oh, okay. Now it's visible.
Yes, sir. Thank you. Thank you. So good morning all. Have a great morning. So this is Vishalatchi. So I'm going to explain and dive into the total topic of hands-on experience on 2D photonic crystal biosensor based on healthcare applications. So before going into the deep manner, we will start from a scratch for a few things. So light. So what is light? Why we are going for light? Why photonics always need light? Because it is a form of, as we know that already, light is a form of electromagnetic radiation which has oscillations between electric and magnetic field. So this is a major phenomena which light has. So that's why we always depend on lights on a speedy applications. So here, if we go for the wavelength of a particular range, the wavelength range normally depends on 390 to 740. But what we are taking in a biosensor, it is different. So I'll explain in later. So according to the quantum theory, light is observed as a packets of data, which is a light quanta packets or photons. So the major part it depends on is photons, which is nothing but light. So here comes oscillations and waves. So what is oscillation and what is wave? Oscillation is nothing but the periodic variation, which is a physical quantity. Of any physical quantity, we should have some periodic variation, and that is called oscillation. And if we go on the topic of wave, and wave is nothing but the extended medium of oscillations, which transmits a disturbance. So light is nothing but a signal which can transmit a disturbance or in the form of data or in the form of white noise. So whatever it is, so it will transmit an oscillation of extended medium. So that is called wave. And here are some definitions that depends on those oscillations and waves. One is amplitude, and we all know that amplitude, which is a difference between maximum displacement and minimum displacement of the wave. And next thing is cycle. So for every wave, there should be a cycle, and cycle, which is nothing but a period. So for a periodic wave, so T is one completion oscillation of a periodic wave, which is nothing but the period of wave. The wave is returned to its original form after the cycle, after one cycle. So this is what we know it already. For that cycle, we need two things. One is frequency and another one is wavelength. Both are interdependent. So we know that frequency is a periodic wave cycles, the number of cycles that the periodic wave undergoes per second. And the wavelength is nothing but the distance between the peak to the next waveform. So these are the basic parameters we are going to use. You might have think why it is needed in this session, because we are going to see that in our outcome of a biosensor. So please be careful while we are reading in a slide. So this is the two representation of oscillations and wave. The first thing is, if we have the fixed time and what is the parameter we are focusing is wavelength. If we have fixed time, we have to calculate wavelength. If we have fixed position, we have to focus on calculating the time period. So these are the two major parts depending on waves and oscillation. And now here comes electromagnetic waves. Since we are focusing on the wave part, waves are nothing but electromagnetic waves. Speaking about the electromagnetic waves, they have vibrating charges, either positive or negative. We know that positive are protons and negative are electrons. So among that vibrating charges, the EM waves can travel or propagate from one place to other place, from source to destination. So this is what the electromagnetic waves can propagate. And EM waves have some criteria behind that. So what are the parameters it depends on? First thing is amplitude. Second thing is intensity. Third is frequency and wavelength. So as for amplitude, which is nothing but electric or magnetic field of its magnitude. So the total magnitude of electric and magnetic field, which is nothing but amplitude. And second thing is intensity. Intensity is nothing but directly proportional to square of the amplitude. And frequency and wavelength we just seen before. So these are the 4 parameters we should focus on electromagnetic waves since we are speaking about light. So as for definition, so what is electromagnetic waves? It is nothing but the range of frequencies. The range of frequencies, what we are using here is the electromagnetic waves. So it can travel at the speed of light, which is 3 into 10 power 8 meter per second. So this is the basic things about electromagnetic waves. So this is a diagrammatic representation of electromagnetic waves. Red color is nothing but electric field and blue color is nothing but magnetic field vectors. So this is what the electromagnetic waves can propagate from one medium to next medium. So the 2 golden spots are nothing but molecular dipole. So between the dipole, the electromagnetic waves is propagating. So this is just a diagrammatic representation for understanding. And here comes polarization. So this is the better characterization we can explain in the part of polarization. This is nothing but the vibrating atoms. When the electric charges started to move inside the atom or a material, the vibrating charges can be produced due to polarization, either vertically or horizontally. That's why the image here is representing vertical polarization and horizontal polarization. So it depends on the propagation, how the light is propagating from one to next. And here is light in transparent media. So how light can behave in a transparent media. So now we can take glass or any other transparent media which can transmit light. So here we focus on various materials. Media is nothing but various materials like silicon, glass, or water, air, anything. So it is like various materials. The speed is given in the terms of parameter. What is that called? Which is refractive index. So the major thing we are focusing in the research is refractive index. So that is why I'm explaining from the scratch. This refractive index is nothing but N. So this N will take part throughout this research by providing light in the manner of phenomena called as total interrefraction, refraction, diffraction, reflection, etc. So these are the major phenomena that depends on light. So the diagram here representing that wavelength and speed of light, because the refractive index using here depends on the velocity of light and the velocity of light in the medium, in air and in the medium. So this is a diagrammatic representation of producing refractive index here. And next thing is bending of light. So what happens when the light started to bend? We know that light can travel in a straight line. What happens when it bends? How it bends? The light can bend when it is inserted into the medium. It can reflect or refract. So this is what happens while we introduce the medium into the light. Light can bend. So light rays bend when traversing the boundaries between media with different refractive index. So this is what the major thing. Here comes the Snell's law. We know that we have all studied about the Snell's law, which is N1 sine alpha, which is equal to N2 sine beta. This is nothing but a Snell's law. This Snell's law speaks about the light can travel from one medium to next medium. It gets bent. This bending of light that makes the refractive index here. So it will change material to material. That's why the value get changes because of refractive index. This is light refraction. So what is a major thing behind that light refraction? When the wave moves from one medium to other medium, the light speed should be different. Of course, we know that because the material is different, the light speed gets different according to the material. What happens when it travels through some different kinds of material? It produces wavefronts, which is nothing but the particular specific wave part of the light nature. So that is called wavefronts. The red color I have quoted is nothing but a wavefronts. This wavefront is the wholesome responsibility of the boundary conditions between the two media, because we will calculate in our software while we are calculating the outcome, we will calculate boundary. So that time you will understand what wavefronts can do, what light can do in that. So these are some of the examples of refractive index I have quoted here. There are so many optical materials. So for each and every optical materials, we have different refractive index. Like I have shown in the tabular column, which is medium and N, vacuum, air, water, glass, diamond, and gallium arsenide. Everything have different refractive index. We are going to use those refractive index for our final outcome. Here comes the total internal reflection. We have seen, so far we have seen refractive index, which is refraction. Now we are going to see total internal reflection. How it gets related with. Why we are going for total internal reflection now? Because of confinement of light. When we focus on light, that should be confined inside the material. We have source, we have material, we have result. So these are the three things, whatever the research might be, these are the three things we should have some basic idea about. So we have talked about source, that is light. If light is passing into the material, so what might be the different things it can create inside the material? One is refractive index that can make the variation in the material while providing the outcome, and another one is light confinement. This light confinement can happen behind this phenomena, which is total internal reflection. So if light traveling inside the medium with higher refractive index than the surrounding medium, which is not called total internal reflection, which is called critical angle. So if that critical angle is concerned, we have to compare that critical angle with the angle which can be reflected. So an angle which can be reflected, which is greater than the critical angle, that comes the total internal reflection. If your light gets totally internally reflected, you can come to the point that light confinement is clear about the material, and we have a perfect outcome, as not as an ideal outcome, but we have the expected outcome, what we mentioned above. So after the total internal reflection, how it comes with the waveguide and fibers. As we know that the angle of reflection, which is greater than the critical angle, is nothing but total internal reflection. So of course, our light should be confined with this condition always. First thing. Second thing, the confinement of light from one direction in space in or space out, which also depends on total internal reflection. So this is the basic condition used beyond it. So now, what is photon? Photons are, we know that photons and electrons, they are different. Photons are very small packets and provides fine control throughout the applications. It is massless, and it has minimum size to the structures so that it can penetrate very easily. And it can travel through the straight lines. That's why it is very fast. We know that nothing travels faster than light. And it can also oscillate very fast. For that, that is the only reason the good start for telecommunication happens in a photonic industry. So this is a basic telecommunication criteria that happened initially in the photonic industry, and now comes there is a so-called healthcare, so-called military defense, etc. and etc. There are so many applications, wide range of applications that is happening now. But telecommunication is a start from the photon. So how the word photonics explained? So photon is different. That is package of light. So photonics is different. Photonics is a technology, and this technology has two things. One is generating, and another one is harnessing of light. So generating and harnessing light is called the photonics technology. So by having this criteria, generating and harnessing light, the light should have some medium. So when it comes to the medium, light can change its phenomenon like emission, transmission, deflection, amplification, and detection. So you can consider any of these parameters while we are going into the research. So this happens, this transmission, deflection, amplification, everything happens when it comes to the application part of optical components and instruments, or lasers and other light sources, fiber optics, electro-optical instrumentation. So each and everything is a hardware and electronics, and we are supporting that. This photonics is supporting that. So this range of applications started from two main categories. One is communication, another one is information processing. So these two are the major application, will give a good start in a photonics technology. And if you want to get into the research, or if you are the early researcher, you can focus on these two applications. One is communication and another one is information processing. So why photonics? Photonics, as we know that it is a technology, we know that, but this technology have signal processing, transmission, and detection. Transmission is nothing but input source. Signal processing is nothing but the material what we are going to design, and the last is a detection, which is outcome. So these are the process that speaks about the technology called photonics. And for this is a one reason why we are going for photonics. And the second reason is optic rays can carry far more data. The amount of data and the data, how fast it can travel from one place to other. So these are the two things we mainly depend on optics, and that's why we go for photonics. So these are the two reasons why we go for a photonics. And why not electronics? Of course, we are not opposing electronics here by choosing photonics. We just want to coin the word. First, let me explain that initially. Photonics is coined from the word electronics, and electronics involves control of electron charges. Photonic involves control of photons. So these are the primary difference between electronics and photonics. And what photonics will do to the electronics? Photonics will provide shoulders by providing help or extra applications to the electronics to move or emerging into the evolving world. So this is the main category of photonics to support electronics. Photonics is the booming technology and always exploring the technology with electronics, not without electronics. And here comes photonic sensing. So far we have seen the scratch of light, photons, photonics, and everything. So we can conclude that photonics have something in our part. Now we are going to deviate our topic, entirely different thing, which is photonic sensing. Like why I have mentioned different thing is, we have so many departments in photonics, so many criteria, so many categories. There are so many things in photonics. It's like an ocean. So among that, we are focusing one thing, which is sensing. So what is photonic sensing? What it does in the world? So photonic sensing is nothing but enabling technology that have two categories. One is general purpose characteristics. Another one is technology purpose characteristics. For general purpose characteristics, it can focus on transistor integrated circuit, like photonic integrated circuit. And for technology wise, it can explain about communication, information processing, and data storage, particularly in health and medicine, energy defense, and homeland security. So these are the major criteria we have to live in our country for these primary things. So that is why we are going for the photonic sensing part. And these are the three major wide range of applications. One is the basic applications of photonics in the left side, and the right side is daily life photonics, and here it is emerging applications of photonics. While you are choosing a topic in the research, or while you are in the initial state of writing your paper, so please focus on how to integrate the basic photonics with AI or augmented reality, whatever it is. You have to select photonics with application like implementation. What I mentioned, implementation is nothing but artificial intelligence or machine learning. So you can integrate your photonic sensor or your photonic sensing, whatever the device might be. You have to integrate your device with machine learning part or artificial intelligence part. So that is what the flow you are going to follow up throughout the process. So be aware of it while choosing photonics. So now comes the topic of main building blocks of investigation. So the main building blocks for investigation is these 6 things. If you understand these 6 things, you can use the software very easily. So first thing is light source, which is nothing but the input you are giving. And second is guide light. You have to know how to guide the light. And third thing is modulation. Modulation is a signal processing, nothing but a signal processing. And photo detection, which is the outcome part. What should be the outcome you are choosing? And fifth one is a low cost assembly. This low cost assembly will decide whether your project or your work is going to stand in a market or not. So this is what your low cost assembly speaks about. And sixth thing is intelligence. As I said before, if you want to integrate your device with AI or machine learning, this intelligence must be the extraordinary part. So this is an example of photonics engineering. If you go on any place, so this is a basic thing. You always have it in your hand, and this is the best example. Will speaks about why you go for the photonics. And this is future photonics. So these 3 things will be always be the future of a photonics. One is high speed fiber optic communication. Networks and optic communications will be the first thing. And second thing, health monitoring and diagnostics. So this is the second one. And third one is manufacturing control and processing. These 3 things are going to rule the world with the photonics. So if you want to start with the research, you can choose from these 3 topics with machine learning or artificial intelligence. And now comes the photonic biosensor. So here start from my topic. I have done my research. I have done 4 works so far. So all the 4 works have been used by this photonic biosensor, particularly photonic crystal biosensor. I will explain it further. So what is biosensor? It is nothing but an analytical device which incorporates biologically active element. That biologically active element is nothing but analytes. That might be blood analyte or urine analyte or whatever it is. That might be the active element with an appropriate physical transducer, which is nothing but the physical transducer is nothing but your biosensor device to generate measurable signal proportional to the chemical species in any type of sample. So this is the total device. We can provide a light source as an input, and this incident light will pass on to the analyte you are choosing, and that analyte is placed in a biosensor, and it will provide the output in a detector. So this is called this is called the total biosensor. And these are the steps we are going to follow in our software, what we are going to see in the future, which is Gaussian light as an input, optical sensor as a platform, which is a device, and photo detector as an outcome. FDTD is an analysis at the backend process, and display, which we can choose whatever the display might be, but we have to choose on your own. Now, what is photonic crystal? We can see, we just saw everything about photonics and related applications. Now, what is photonic crystal, which is a sub branch of photonics, which is the entire platform of crystal part. As we know that crystal, which is nothing but the periodic arrangement of atoms. We cannot say that it is a device. I'm just saying that it is a crystal. When the crystal is going to be the device, how we can make the crystal to act as a device? By providing defect engineering. What is defect engineering? So defect engineering is nothing but making cavities or removing the rods, making holes or making cavity to the device, which is line defect or point defect. So we have two defects in defect engineering. One is line defect, another one is point defect. So by creating that defect, we will make the photonic crystal as photonic crystal biosensor or photonic crystal device. So this is a major thing we are going to provide here, and we are going to make the photonic crystal to act as a sensor. As I said earlier, this is a periodic arrangement of atoms or of any photonic crystal, one-dimensional, two-dimensional, and three-dimensional. This is up to our part. And the major thing going to act is refractive index that make a device changes that happens in the outcome. That is depends on refractive index. So here is a basic structure. A, which is the configurations used in this photonic crystal. One is rod in air and another one is hole in slab. So these are the two configurations. And the B explains about the slab and the material. Here I have chosen air hole. Around the period is nothing but, I have told you already, period is nothing but the wavelength we have mentioned earlier. And we have chosen the material of silicon. So this is the entire slab we are going to make to act as a device. So here comes the E, D and E, which is nothing but photonic band gap, which shows how far the light can be confined into it. So this is called D and E. And F explains about the defect engineering I have told you just now, line defect and point defect. You have to remove the rods as a point or as a line. So these are the two things as a total photonic crystal structures and their optical properties, which can be explained now. And this is an example. Detection of respiratory viruses. We have chosen different types of respiratory viruses, corona, adeno, etc. So these kind of virus we are going to detect in a device. So this is what the major motivation behind it. And here we have designed two things. One is hexagonal double ring, horizontal double hexagonal ring resonator, and another one is vertical double hexagonal ring resonator. So these are the two structures. We are going to compare the results, and we are going to code the results at the end part. We have used Opti-FDTD algorithm, which is a software I'm saying, Opti-FDTD, and we are going to integrate it in a machine learning part. We have achieved 97% accuracy by using the machine learning algorithm, which is nothing but naive-Bayes algorithm. And you can use your own algorithm to achieve better accuracy by comparing with the past results. So this is the motivation here. The motivation is a small size sensor. We have to provide small size sensor and also with low power consumption. This is a major motivation. And second thing is going to integrate with machine learning and provide better accuracy. Third thing is to avoid earlier death rate. If we find it earlier, we can avoid the death rate. So these are the three things behind the motivation. And this is a proposed structure. So the proposed structure is, which I have mentioned the name, horizontal double hexagonal ring resonator and vertical hexagonal ring resonator. So these are the two structures we have chosen and compared. The comparison parameters we have to calculate is quality factor and sensitivity. As far as biosensor is concerned, we have to focus on these two parameters. One is quality factor, which is nothing but the ratio of resonant wavelength with respect to the ratio of full width half maximum. Wavelength, change in wavelength versus full width half maximum, which is nothing but quality factor. And as far as sensitivity is concerned, sensitivity is defined as change in maximum resonant wavelength shift to the change in refractive index. So change in wavelength with the change in refractive index is nothing but sensitivity. So we have to calculate quality factor and sensitivity. So this is PBG calculation, which is photonic band gap. We have two modes here. One is transverse electric modes, another one is transverse magnetic mode. So you have to check whether you are getting band gap in either of the modes. So this is a band gap that I have spoken already, which is total internal reflection. I hope you all remember that thing. This is the light confinement which compared to the total internal reflection, if you got this photonic band gap, you can provide the assurance that your light get confined within that periodic structure of sensor or device. So now is the results and discussion. So this is we have got two results for each sensor. So this is our first result. We have compared normal blood with TB, corona, HBOV, influenza, and adeno. So these are the respiratory viruses we have compared with the normal blood, and it provides some shift. So as I have told you about quality factor and sensitivity, so it depends on this wavelength part. So it depends on the outcome part. You have to consider this outcome as to calculate sensitivity and quality factor. So no need to confuse here. So this is a chain of process. So you will understand step by step. So here is a second result, which is also the comparison part of TB, corona, HBOV, influenza, and adeno. So we have compared all the refractive index with these two structures, and we have to provide the better amplification, better sensitivity, better quality factor. So this is the parameters we have to compare here. And by considering the parameters, and we have to fetch the data of quality factor, sensitivity, and amplitude. So these are the data we have to fetch it from the software and integrate into the machine learning algorithm. And this is the outcome of machine learning algorithm. We have used naive-Bayes algorithm here. And as far as naive-Bayes algorithm is concerned, we have included these data in the algorithm. By training and testing the data, we achieved the accuracy of 97%. And these are the representation diagram of our training and test data. Once we are providing, if you browse the file of data of normal, it will provide you which is normal. Okay, after getting test file, it will give you the data is normal. And what if we are changing the data into influenza, corona, or TB, anything, it should provide you that yes, this is the infected blood. This is not a normal blood. So this is a major representation of the naive-Bayes algorithm classifier. And here is a conclusion. So we have concluded everything here, as we have provided 2D photonic hexagonal ring resonator sensor, and among these two types of sensor, we have compared quality factor, sensitivity as outcome parameters, and we have fetched the data from the the sensitivity and quality factor data from the outcome, and we have trained and test the data by using the naive-Bayes algorithm. And after that, we have produced the result of 97% accuracy. So you have to compare those things with the past papers or existing work. You have to do your better results according to that. So by that, we have provided low power consumption, small size in the device, and at last, we have provided the integration of machine learning into the device. So this is the conclusion part. I think so far I have cleared one particular direction of light from photonics to photonic crystal. So thank you so much. Let's move on to the hands-on experience now. If you have interested in doing research, or if you want to ask any doubts from that, you can feel free to reach out me on my LinkedIn. I will always be there in LinkedIn, so you can reach me out. You can save this link for your further use. So thank you so much.
So now, Vishalatchi,
Yes, ma'am.
you start hands-on, but before that, take few questions. Okay.
Yes, ma'am.
Okay. So the participant, if you are having any doubt, you can ask now. Then otherwise, next she will go for the hands-on. So any participant?
Yeah, I have a doubt. Hello.
Yes, sir.
Madam, can you tell me how you are capturing the data and what will be the format will be storing your data?
Ma'am, the capturing of data, just we are move the data as a tabulated data, because since it is a data, not an image, as you know that there are two things. One is image classifier, another one is data classifier. So we have chosen the data classifier since we are taking tabulated data into the format, and we are using your algorithm to fetch the data. So these are the two things we have done so far.
Can you show what are the parameters you have used in the data set? How your data looks?
Yes, ma'am. We can. I will show the parameters now. Okay. Oh, it is presenting screen.
Your screen is not visible. Now it's visible. Okay,
Okay.
Vishalatchi.
Yes, ma'am. So, yes, ma'am. This is the two parameters we have used, quality factor and sensitivity. Since if you want to add up parameters like power consumption or amplitude into the part, you can add up so many parameters into that. But so far we have had only three. One is amplitude, quality factor, and sensitivity. So these are the three things we have used so far.
Okay. What about
Hello,
the
ma'am.
data set? Can you put the capture data, how you train with the KNN, K means you have told, no?
Naive Bayes algorithm. Yes, ma'am.
Base algorithm. Can you
Um,
show that data
Uh,
values?
Actually, this is not the system I'm having here, ma'am. Maybe if you want, I will share to Preeta, ma'am. You can see it later.
Okay.
But I will tell the technical part what I have done so far. Since you have achieved the wavelength, right, ma'am? So, for example, if this is outcome. This is, for example, this is outcome you are getting as a representation part. For now, you have to see for normal blood, and you have to get normal blood result. Correct? This is
Yes.
this is the consolidated results I have shown. But in reality, once you are going to get the data as an outcome, you have to get it by individual format, like normal blood, like TB. So you have individual outcome on your hand. For each and every outcome, you have 4,000 data or 4,000 to 6,000 data on your outcome part, which I will show you in the hands-on experience. So now we can understand what is the real part I'm saying about fetching data and providing into algorithm.
Okay, sure. Thank you.
Thank you.
Hello, ma'am. Can you explain how to analyze the band gap?
Yeah, sure. Can I explain it in hands-on experience, because everything depends on that.
Okay, ma'am.
Yeah. Any other question regarding the photonic band gap, or else you want to see how it works?
Yeah, we want to see how it works.
Yeah, I can show you in hands-on.
So any more question is there, so that now she will start the hands-on. So I hope this session will be the best session, because I am very happy that people are taking interest and asking the question. It means they are listening. This shows. So any other question is there?
Is it both the tools need to be installed?
Yes, ma'am. We have to install.
The tools which is shared is of 32-bit resources. Is it sufficient,
Yes,
or we
ma'am.
need to use it as 64-bit? Is it something is there?
32-bit is enough. If you are a beginner, you can use 32-bit for your concern. Then after you are an expert, you can use 64-bit. There is no more much difference between those things. Just it's the learning platform, ma'am. Nothing more than that. Yes, ma'am.
So I think by seeing their interest, Vishalatchi, you can
Yes, ma'am.
start from the beginning, so that they will do it by their own.
Yes, ma'am.
Then
Sure,
it
sure.
will be a very great achievement, and I will be happy that my FDP conduction is successful, because few participants, they learn something. They
Of
will
course,
have the
ma'am.
take home really. Okay,
I'm also very happy, ma'am. Really
because
happy.
this is the fifth day, but till now I have not seen the involvement of the participant in such a way. So I'm very
Thank,
happy, really.
thank you, ma'am. Thank you so
Okay,
much.
so you start that way. Okay.
Yes, ma'am. I will start with the hands-on experience.
Yes. Okay.
Remaining doubts you can ask after the hands-on experience. I will explain it later.
Or during the hands-on also you can ask.
You can raise the hand and you can ask. Sure,
Yes.
sure. Yes. Can I share my screen?
Yeah.
I'll start with this. Can you see my screen? Is my screen visible, ma'am?
Yes, it is visible.
Okay. So, guys, I'm going to use Opti FTTD 32-bit designer here. So let us start with the basic design first, so that you can easily catch up things. See, if you want, you can note it up. Just go to the file, go to new.
Note.
So this is the initial properties. Um, this initial properties have default waveguide, wafer dimensions, 2D wafer properties and 3D wafer properties. So my research goes with 2D wafer property. So I'm going to select 2D wafer properties with air. I have told you already there are two configurations. One is rod in air, another one is hole in slab. Now we are going to see rod in air, which is very easy for the beginner to understand. So I'm going with the rod in air configuration and have selected the material as air here. And this is a wafer dimension. This is not particularly to be concentrate on. You can select anything. So now I have selected 10 cross 10 as length and width. And see here, there is one tab which is profiles and materials. You have to select this profiles and materials. Don't search here. Here it is showing like with the blinking part. So this is profiles and designer. This profile designer, we are going to provide input that make the material to differentiate as a device or sensor or etc. So for that, we have to provide new dielectric, that is material. We are going to create one material for ourselves, since we are going to make the photonic crystal act as a device. So I'm going to I will give the silicon photonic refractive index like 3.45, for example, approximately 3.45 I'm giving. After providing that, you can change the name like silicon. And okay, I have stored it. You have to select the store. Okay, so we can close it. You have created material, silicon and air. This silicon is a rod and air is a slab. Rod in air, that is it going to act as a rod in air configuration. So now we have to create channel, not fiber. We are going to create channel.
Can you repeat little? Can you go a little slow?
Yes, ma'am. Sure. Can I come from the starting point, or
can you repeat once again after the file and the property settings?
File and the properties? Okay. This one, initial properties.
Yeah, initial properties.
Okay, so this is the initial properties. We have to focus on two things. One is wafer dimension and another one is 2D wafer properties. This default waveguide, since we are using channel as an example, it will be already there. If you want to change it to fiber, you can change if you change the project. And now we are focusing on photonic crystal. Channel is important. Second thing is wafer dimension, length and width, which is not to be particularly concerned about. You can choose whatever the length and width might be according to your sensor you are creating. 2D wafer properties, we are choosing rod in air as a configuration. So we have select the material to be air. So far we have done initial properties. We have to move on profiles and materials. We are going to create a material which is a total profile. That is why it is called profiles and materials. So if you click the profiles and materials, you will have it in your taskbar. You have to select like this. This is your designer, Opti FTTD designer. Here you have profiles and materials. First thing, we are going to create materials here, and then we are going to create profiles. So this is what the steps looks like. We have to select dielectric, right click on it. You will have column new. You have to select it. If you select new, this one will get appear. This tab will get open. So you have to select your material, whatever graphene, silicon, whatever the material you are using. you can select that material and its refractive index. So as I told before, refractive index is an input material going to change the medium. So silicon, which is 3.45, you have to select store. Once you click the store, just close it. So this is silicon for dielectric. And now we are going for the profiles. As for profiles are concerned, we have to select the channel, not fiber. If we select the channel, right click on it, click new. If you click new, this tab will get open. Okay. So far, so good.
Yeah, it's clear.
Okay, ma'am. Can I continue?
Yeah, sure.
Yes, ma'am. So this is what the channel looks like. You have to change the channel according to your name, silicon, and we have to select silicon. So this is the channel for our material. Since we are having 2D profile, so we have to select 2D material as silicon, and everything needs to be set. There is no change here. You just click store. Okay. So our material have created and channel have created. So we have created both. So after creating the both, you can minimize this. So we have created our profiles and materials and provided initial properties, and you can just click OK. Okay, so this is 10 cross 10 length and width. If you want, you can zoom in. Okay, this is a wafer thing we are going to use as a platform for a sensor. So now we have to create photonic crystal. See here, there is a dotted icon here. If you move over the icon, it will show PBG crystal structure. You have to select PBG crystal structure and just click. So after that, we have to go, we are going to provide properties of this crystal. We are going to provide those properties. For that, you have to select. If you want to come back to the arrow mark, you can use two things. This is a normal arrow mark and this is PBG arrow mark. It will this PBG will gets into particular cell or particular part. This arrow is for normal thing. You can use it for wafer and also the crystal. So you have to double click. I have chose this arrow mark. Don't get confused among those two. You have to double click on the particular rectangle square box. This is crystal lattice properties. So while providing, it is up to you, up to your dimensions. So I will follow mine. Here I am going to give 2D hexagonal. See, I have changed lattice properties, which is 2D hexagonal. And now it is lattice dimensions. I'm going to give 0.5, which is this scale is nothing but the distance between the two cells, two crystal. Okay, so here I'm going to give 20. These are the number of crystals we are going to place, A and C. Since it is a two-dimensional, B is not enabled. Okay, then I'm going to atom waveguide in unit cell. We are going to provide the properties for unit cell, which is single crystal. You have to click new. I think atom waveguides in unit cell. Below that, you having new. You have to click on the new, and this elliptic waveguide properties tab will get open. And once it get open, you have to focus on radius, major and minor radius of that particular crystal, because it is circle in structure. We are going to provide radius for those crystal. So I'm giving 0.7. If we want, we can change. So you have to check whether you are having your profile. We have created channel silicon, right? So it should have called here as a profile. You should select that profile. So these are the two things you have to do it for the elliptic waveguide properties. Once you have done, you can click OK. And after that, everything is fine now. You can click OK. So this is what it looks like. So we can change it. If you want to edit, you have to click, you should not click new, you should click edit. Careful, you want this often. You have to click and change the radius. I have changed. Right. Okay. All right. Hope it's fine. Okay. Okay. Can we reduce this? We can reduce the number of cells. Again, if you want to change anything in the structure, just double click on it. I'm going to reduce this numbers. Just click OK. Fine. Hope everyone understand this. Can I move forward? Do you have any doubt here?
Here, I will ask
Yes, ma'am.
any participant is having any doubt, because some of the participants, if they are doing along with her, they can doubt,
Yes,
so
ma'am.
that she will go to the next level. I
You are
think no.
setting, hello,
Yes, ma'am.
you're setting some of the values vertical and horizontal in the expression.
Yes, ma'am.
Based on what condition you are assigning the values?
Actually, ma'am, I didn't set values for expressions that for horizontal and vertical. We are just providing, see, this software is a backend processed already. We no need to provide any expressions or formulas over there to speak about. So we can provide only the radius. We can change the properties of the crystal. So far we have achieved. And this is a trial and error basis, ma'am. So I have done so many works, so that's why I can understand. So this is what the radius might be. This is what the distance between the crystals might be. So I am giving on my part.
Is it any standard distance we need to specify over here?
Not exactly, ma'am. Not exactly. That depends on your device you are choosing, because people used to have filter device over here. People used to design sensor over here. So it depends on the device you are choosing and the dimensions of the device they have used in the past. So it depends on the existing work. There is no standard to follow this and all.
Okay.
Yes, ma'am.
I think Vishalatchi, you can give the range. There is no standard to follow, but range can be given as per participant questions. I think so. Some
Oh,
range
yes,
will be given.
that's fine.
That range you can tell.
I can tell the range if it seems
Yes.
to be very important.
Yes. Yes. Yes.
So you can select 0.5, but my standard as far I have done so far, I have chosen 0.5 as a level. I can show you that one. So this is the crystal lattice properties. Here you have types of lattice properties, which is rectangular, hexagonal, rectangular, 3D and 2D. For that, you have to choose accordingly. According to the design, you have to choose. And this scale, this is nothing but the lattice vector, which is the distance between these two crystals. This is called scale of lattice dimension. I have chosen always to be 0.5, since that I have followed my existing work to be 0.5, so I have followed the same for my work. You can change to 0.5, 0.55 and 0.6. So up to my experience, I can tell 0.5 to 0.7 you can use. If your distance between the cell getting longer and longer, if the cells move far away, your light will not get confined. So far I have gone through these things. I will say that you can reduce the as much as possible. 0.5, 0.56, 0.57, that is fine. If you go for 0.6 and 0.7, light cannot be confined and you will not get a photonic band gap. It will get dispersed over the place. So this is a particular scale you can choose. You can follow whatever I have done. You can follow the same for your structure too. Is that fine, ma'am? Is there anything I have to be add up?
No, I think fine now. You can go to next level.
Okay. So we can move to next level. Just so we have created a photonic crystal. As this is a crystal, this is not a device yet. Once we have to provide the defect engineering over here, we are making this photonic crystal as a device. So for that, we are going to remove crystals by making a defect. So here I'm going to provide line defect. Watch carefully. You might have get confused here. I am placing the arrow here and right click on it. It will show these things because I have selected this arrow mark. This is for wholesome. So if it doesn't works, we have to click on the structure and click this PBG structure properties. Once you have selected, now I'm going to create a defect in this crystal by removing the rods in the entire line.
बैंक के जाना है, बस 5 मिनट का काम है, बैंक के जाके आना है बस। तो कितने लगी बैंक की जाना है?
I hope someone is speaking along with me.
अच्छा ठीक।
Okay. So now I will continue.
I will request all the participants to mute. Yeah.
Thank you, ma'am. Thank you. Here I'm going to right click on it while placing this arrow here. See here, you have to place the arrow whichever the rod you are going to remove. I'm going to remove this rod. So I'm going to place this arrow here and just right click on it. Provide cells off. So this is what we are going to do for removing the rods. So I'm going to remove the entire crystal line, placing on the wafers we have created. So I'm just providing cells off. Follow me. If you didn't get the point, you can ask me now.
Can you repeat once again regarding setting the defecting cell?
Yes, ma'am. So here are the two arrow marks you are having. This is for normal crystal properties. Total crystal properties you can change by using this arrow mark. If you are going to create defect in this crystal particularly, you have to select this icon. This is PBG crystal structure cell editing tool. This icon represents that one. So you have to select that first and then move on to the place where you are going to create a defect. I am going to create a line defect in this crystal. So far I have created this line defect. I will repeat this again. You have to place the arrow mark on the right side of your crystal and just right click on it. You will get this tab and you have to click cells off. Okay, so I'm again repeating the same thing. See here. Okay, I'm giving cells off. Okay. Right. Okay. Fine, ma'am. Can you get it?
Yeah, got it.
Okay, so I'm just moving forward to the next step. So we have created a defect now. Now we are going to see how it will act as a device. So for that, we have to provide input, right? So we need some light source. For that, go to the draw. Go to the draw section. You have vertical input plane, horizontal input plane, and point source. These are the different types of input planes here. And now I'm going to select vertical input plane. You just click on it. You will get an input plane over there. You select that input and just click over here. It will be placed. After placing that input plane, just double click on it. You have this tab get open, which is input field properties. Here you have two waves, continuous and Gaussian modulated continuous wave. I'm going to modulate my input with Gaussian modulated continuous wave. And for that, you have to provide, it will automatically select the things. You can have it as such. No need to change any position or something. You can follow the same. Here I'm going to 2D transfers to check the half width maximum, whether it is placed as half 0.5. So I have checked it. If you want to change this half width or tilting angle or center position of the plane, input plane, you can click auto. You can just click here and you can change. Just click here and change. So this is up to you whether you have to change or you can have as such. As far as the software is concerned, there is no need to change anything because they have the setting properties as a central part. If we want to change exactly, if your existing work they have done differently, so you can change this. Otherwise, you can follow the same whatever they have given us already. So this is local and amplitude is going to be 1. We are going to compare for value 1. And this is very important. You can change wavelength according to the device you are choosing. Some device can use 0.65, 0.67 within that visible spectrum. And since it is a biosensor, we have chosen 1.55, which is 1550 nanometer wavelength. And this is this software works under micrometer. So you have to change if the values are in nanometer. Please be aware that you have to change it into micrometer while using the software, because throughout the software they have used micrometer. Since I have provided 1.55 micrometer and just click OK. I have set up the input plane. I have created the crystal. So here comes the output plane. We need that. For that, we are going to provide the same draw section. Go to this observation point. So these are the observation or outcome we can analyze. You can choose vertical, horizontal, area, whatever you want. So here I want to choose observation point since I am going to calculate sensitivity and quality factor over there. So I am going to select observation point here and just placed over there. You can select so many observation point. If you want to observe this area, if you want to observe this one here, there, you can place observation point anywhere else. So now I'm going to use 2 observation point. So the next observation point I'm going to place here so that I can show you difference between those output. So these are the 2 observation point I have placed. So far I have done the input source, outcome, and everything. I have created it. Now we are going to analyze it. Before going to that part, we have to save this first. Save this. As FDTD. Save here. I have saved. Now move on to the next step. We are going to calculate PBG, photonic band gap. So for that, going to the simulation part, after saving the whole thing, you have to go to the simulation part. Here you have PWE band solver parameters. You have to select this. This tab will get open. I think you are following the same. Did anyone or behind it? Do you have any doubts so far? Can I continue?
Anyone want to know about the band gap? Because band gap is very important role in photonic crystal.
Yes,
So
ma'am.
anyone want? So otherwise you can just tell role of band gap in optical sensor.
Yes, ma'am. The
Oh,
photonic, yes, ma'am. The
hello, ma'am.
photonic band gap. Yeah. You can.
Ma'am, can you explain how to get a band gap and how can you explain how to analyze the band gap?
Yeah, sure. So this is the steps. You can follow the steps now. You are in the right place. Okay, this is a tab. You can see the PWE parameters tab. So here you can select two modes. This is up to you. This is just a polarization. Whatever the thing you are going to get an outcome, this is just the outcome part you are going to change. This is in your hand. I am going to choose TE, transverse electric mode, and here you have to check whether it is 16 cross 16. The mesh should be 16 cross 16, and it is automatically will be provided there. There is no need to change. And here is a K vector path. So this is what you are going to select. We have created hexagonal lattice. So we have to select hexagonal here. And after selecting this, mm, mm, click OK. And now I'm going to, where is run? Wait, here is run. We have selected that, and now we are going to run the band gap. Okay, we'll see whether we get the band gap or not. Good. Okay, fine. We got the band gap. So you have seen how far we have selected the parameters. And finally, we got the band gap here. We got three band gaps over here. See, 1, 2, 3. So here they have explained band gap 0, band gap 1, and band gap 2. 0 is nothing but the initial part. So no need to get confused. So there are three band gaps, and they have provided you the values of the range. This is the frequency range. They have given 0.552451 is 51 is nothing but the frequency range between here to here. So this is a gap, and this is a difference between those range. This is nothing but the difference, and this difference provides you the width of the band gap, how far you got. This is 0.3, and this is 0.05, and this is 0.002 because it is very thin. But so far we got three band gaps, which is good. We can say that the light is confined throughout the device with a good manner. The distortion is less because of the light confinement, and this is a result we can show as a photonic band gap, particularly for the sensor, because sensor it works to provide sensitivity. The sensing part is a major part. For that, light should be confined in a proper manner. For that light confinement, we go for photonic band gap, and here is a photonic band gap. So I have explained the photonic band gap. Here, any doubts?
Ma'am, how can we identify that that is for the particular observation point?
That is an outcome. So that is the next part. I'll say the next part. So far, photonic band gap is concerned. Is that everything fine with that? Can I move to the next
Okay,
step?
ma'am. Okay, ma'am.
Yeah, sure. So I have created this PBG. Now it's all set. Now we are going to run this total device. Go to the simulation. Select 2D 32-bit simulation parameters. We have
Hello,
selected
ma'am.
Yes, ma'am.
Ma'am, why to calculate the band gap and what is its significance with respect to sensitivity?
Like I said before, we got the parameter called total internal reflection, right? So I have explained it earlier. So for that phenomenon, the thing is, we have open device, we have so many materials over there, we have created defects over there. Why we are creating a defect in the crystal? Without that defect, the crystal cannot be a sensor or any filter or any device. So we cannot mention it as a device. It is a crystal, correct? So in that sense, that is to be considered. Light is traveling from one place, that is the input to the output destination. It is traveling throughout the material with the defect. So how come you can identify? How come you can say that light is confined? Because once your light is confined, you can openly say that you have got less dispersion. To provide that as an outcome, you should mention your photonic band gap into your research while we are going to the crystal part particularly. And as you have asked how the sensitivity meant here, so far we are calculating, everything depends on the light, right? So everything depends on the light, what is traveling throughout the crystal. Sensitivity is nothing but, I have told you already, that is a formula we have mentioned, which is nothing but the wavelength it depends on, correct? So change in wavelength. So automatically, if you focus on change in wavelength and changing refractive index, what should be the best part? You can say that light should be confined, right? So this is a scratch. If light is a scratch, light confinement starts from the scratch. Light confinement say that you will have better sensitivity with that refractive index you have provided as input. Got it? Hope I have
Okay.
cleared.
Okay.
Okay. So can I continue?
Yeah.
ma'am.
Okay. Okay, sure. So here I have chosen P, which is transverse electric mode, and this is run for, which is you can untick the auto mode, and you can give your own time steps. I'm giving my time steps to be 3000. You can give 5000. Up to, if you want to wait for 1 hour, you can give 15,000 also. There is no need for the time steps. It will take time, but you will have more wavelengths. As someone have asked me already that how can we get those data from normal blood to the infected one. So here is the answer. If you want more data, if you want 5000 to 7000 data from the tabulated particular wavelength, you can provide more time steps here. If you want to get more data, or for particularly for the wavelength, you can provide 5000 to 7000 or 10,000, 15,000 time steps over here. So it will take around 2 hours or 1 hours depending on your machine. So it will take that much, but you will got your wavelength as 7000 data. So particularly you can use it for machine learning and artificial intelligence too. So I have chosen 3000 here, and you have to check whether input plane and wavelength should be here. So I am providing run. So this is what the light is traveling through the defect. Can you see that? I have provided the line defect. The light is confined. If you didn't get the band gap, the light is not confined to the particular defect. It will get dispersed over the areas around what you have created. So that is why we have created the band gap. So next, this is a FDTT analyzer. So far we have designed in designer, and this is analyzer tab. If you click S over here, your analyzer tab will get open. See, this is designer, this is analyzer. Looks like same, but it is different. This is your structure, and we are going to analyze the structure. Go to the tools here in analyzer tab. Go to the tools. Here you have observation area analysis. We are going to analyze the results. Okay. So you have asked, right, how can we compare observation 1 and 2? Here it is. We have to select. If you want time steps, you can have time. I am going to calculate in frequency. So I am getting calculated with frequency DFT. This frequency DFT, and from the minimum wavelength to the maximum wavelength, I have chosen 1 to 3.1 here, and normalize with the input plane. I have tick the box normalize with the input plane. And after that, provided everything, we have to click update graph. So this is the updated graph from 1 to 3, because we have minimum and maximum wavelength. If we want to focus, because we have focused on a particular wavelength, which is 1550 nanometer, we should be focused on 1.55. So for that, we have to provide this one. So this is the changes happening in observation point 1. And now I am selecting 2. You can select this 2 and provide update graph. Okay. So I am unchecking the observation point 1. So you are getting a good curve over there. If you want to provide any changes, right click on it. Right click on this tab. And these are the things you can do. You can draw over there. I'm going to zoom in because we want 1.55, right? So I'm going to zoom in. So here there is no curve, but you have should be the range. The range should be of 1 to 1.55 or 1 to 2. You should have curves around 1 to 2 so that you can compare how to optimize your sensor while comparing with the existing work. So this can be randomly chosen, but you have to be so particular towards your work. If you are choosing your work to be so particular by comparing with the existing one, you have to choose the parameters what they have chosen and compare with yours. So this is what the observation area analysis, and we have 2 observation point over here. So far I have created this thing. So these are the 2 things. If you want to compare, you can compare separately. Okay, so far we have created the graph. So this is the output. If you want to save the data, you can save data as you have to name it according to the data. I will name it here. FDP. This is observation point 2. FDP 2. So I have saved it. So if you want to open that, I think I have saved it just now, right? You have to double click on the thing you have saved and you have this graph now. Someone have asked how to retrieve the data. So this is the wavelength. If you got, this is a sample wavelength, but if you got the particular answer like 1 to 2, you are getting good amount of curves. So the differentiation of data is good. So you can compare with normal blood, and you can compare with the tuberculosis, compare with the adeno and corona, whatever the infected analyte might be. So you can compare with one wave with another wave by using the data. So I am saying about the particular data over here, and for that you have to compare with another particular data. If you want to do changes in your material, you have to change the silicon as a infected blood, silicon as a normal blood. So you have to change according to your concern. So far I have created the curve and I have shown how to calculate the curve too. Is there any doubts over here?
And here in my WhatsApp, I'm getting this how to create the data set, means from this graph, how you will get x-axis and y-axis values data.
Ma'am, that is there is another tool. You have to use that tool to retrieve the data. You can use Origin Pro. There is one tool called Origin Pro. You can select the data of particular wavelength over there. After getting the data, you can use the data into your algorithm. Yes, ma'am. Any other questions, ma'am?
Can we save this data in the tabular form?
Yeah, we can change. That's what, ma'am, I told just now. You
Yeah,
can have, yes, ma'am. Origin Pro is one software is there. You can install that software and you can save this data over there, and it will provide the tabulation form of the data.
it does not have an option in this simulation tool to have CSV file.
So far, I didn't use this tool to be because I didn't feel like comparatively Origin Pro is good. My seniors have advised me to take that. So so far I didn't use this tool to be the retrieving data as a tool. I think no, we cannot do that.
I think .dat file will be there here.
Yes, ma'am, we can, but I think this print option we can do that.
.dat file, because we
I
were
don't have
doing
any.
that long back. So it was coming the X and Y axis.
Yes, ma'am. Actually, we can see that if you right click on it, if you want to, you have marker. If you have info like this info, it will give wherever you place, it will give X and Y axis data. But it is very difficult to retrieve data as a large amount at a single amount.
No, not like at the point of X and Y axis. It was coming as a full column, X and Y column, full, complete spectrum data. It was coming.
So I didn't use here, ma'am. So I don't know how to do that.
Here you are showing only two data, na? That particular
Yes, ma'am.
where,
Only the particular material data.
like where you are pointing, that particular point you are getting the data. But
Yes,
suppose
ma'am.
somebody want to work in AI/ML, so they want a data set. Now data
Yes, ma'am.
set creation is also a very important thing.
Yes, ma'am. But I hope that Origin Pro, which I have mentioned, that will provide the exact data, each and every corners where you have selected. If you want to select from this to this, it will provide the data particularly for that variations. So I will write on the chat too, ma'am. Origin Pro.
Yeah. So it will helpful to the participant.
Yeah, yes, ma'am. Sure, sure. I'll do that. I will write the chat. Origin Pro. I have Origin Pro. I have few questions in chat box also. Coding link when to use continuous waves. What is the benefit of? So I will answer the chat box questions now. Ma'am, can I proceed with that?
Yeah. Chat box.
So Dr. Vanaja ma'am have asked one question. When to use continuous waves? What is the benefit of Gaussian modulated continuous wave? Ma'am, as far as input provided is concerned, the continuous wave and Gaussian waves, there are near same. The continuous wave, you will the application what you have chosen, that might be the only difference. Like if you are going for a sensor, you are focusing on sensitivity and quality factor. If that is concerned, you are focusing on a particular wavelength, which is 1.55 from the range, if I am saying, is 1 to 2. So if this range is concerned, you have to be very focused on it. So that Gaussian modulated continuous wave will provide you the solution according to it, since it is a modulated form of wave. And this continuous waves, it is the main form of waves, which is not like Gaussian waves. Gaussian waves is a sub branch of continuous wave. Continuous waves we can use as a filter, because we know that a filter is a filter function. We know that it will filter the particular wavelength according to the application, according to the requirement what we are choosing. So at that time we can use continuous wave. It will also it will also speaks about the range, but not the particular range of 1 to 2. It will take more than so many ranges of 1 to 10 or 1 to 5 according to the requirement is concerned. You can change according to it. So continuous and Gaussian modulated continuous wave are not much different. Only difference, we can choose the application with that input plane. So this is the only difference. And hope I can answer that question. And One student have asked after recording, you need recording, we'll send you. And why 3 band gaps is necessary? Can't we get only 1 band gap and confined light? So as for the student have asked this question, 3 band gap, there is no condition for calculating the band gaps. You may get 4 band gaps or 5 band gaps. That is not the condition or criteria we are posing here. The only thing is, if you get 1 band gap, if it is having wide wavelength, I mean the range it travels through it, we have 3 band gaps. But the only thing, the wide range of band gap will decide you that the light is confined at the particular region. So we can say that the frequency of the light, we can calculate it with the outcome should be relied on the optimization. So as we are talking about the optimization part, only the band gap is always depending on the optimization of the biosensor. For that purpose, we need band gap. That purpose, it depends on light confinement. So there is no such criteria that 1 band gap, 2 band gap, how many there is no conditions to get the band gap. But if you are getting more than 1 band gap, it is your device to be get optimized more when compared to others. So this is the only thing. And another question, out of 3 band gap, guide perfect. So we can say that it is a common question, like we can say that when the width of the light confinement, when the width of the band gap is bigger, the light is confined through the particular region very well. So that is the only thing we can relate it to. Yes, so I have answered every question so far. Preeta ma'am, I have answered the questions. Is there any other doubts?
Ma'am,
Ma'am?
what is the advantage?
Yeah, continue.
What is the advantages of using this tool only than compared to other?
Which one? Can you come again?
What is the advantages of using Opti FTTD tool compared to other tools?
Exactly. The thing is, we can use any tool. You can use Opti grating. In Opti itself, there are so many tools. Depending on the source and the materials you are choosing, there are so many things like fiber black grating, surface plasmon resonance, and this is called photonic crystal. So each and every platform have different focusing on the technology. So according to the technology, it may differs. But everything looks like a biosensor, but technology wise it is different and platform wise it is different. So we cannot range the difference. This is best, this is bad, this is not good. So we cannot range it, but we can say that it is under photonics, so it is an emerging technology. It is to be a booming technology. We can choose among that. So better, I have done the research with the photonic crystal, so I am speaking with the photonic crystal. If you want to do the research with fiber black grating or surface plasmon resonance, you can do, and you can see the difference.
So those who are interested, they can collaborate us, our group. People are using SPR, grating, photonic crystal, many more LDR. Okay, so many things, subdivision of the photonics we are working. Okay, so any more question is there? I hope Vishalatchi, you have covered one structure you have handled.
Yes, ma'am. I have handled one structure to the
Okay.
entire outcome. I
Okay.
hope everybody have interest in those structure and photonic crystal part.
Yes.
I'm
They
so
are taking
happy to
interest.
explain the questions they have asked.
Yes, because they are taking interest and asking. That shows the interest.
Yes, ma'am. I'm really happy. I have to thank you for particularly getting into the topic.
No, I think because FDP when we are doing, I want something should be take home. Not only listening, but doing and implementing and publishing paper. That is the main intention of this. So I hope any more question is there, because this was the basic talk. Based on this you can do, and in future also if you want you can connect with us. She is very helpful. She will definitely reply.
Yes, ma'am. Sure.
Okay. Yes. Yeah. So any more question? If not, then we will tell Gerard sir to end the session formally. No more question. Okay.
Thank you for all.
Okay.
Thank you, ma'am.
Okay. I will tell Gerard sir to end the session formally.
Okay,
Gerard
sure.
sir. Okay, he's not there. Maybe no issue.
And ma'am, this is my request. Can you please switch on the photo section? Can we take one photo with all
Okay.
the students?
So
And
you remove the this one which you are sharing.
yes, ma'am.
Sharing part you remove so that everybody can switch on the camera. And yes, so may I request everyone to switch on the camera as per her interest. Yes.
It was very good section.
Thank you so much,
Ma'am.
ma'am. Thank you.
Thank you, ma'am, Preeta ma'am, for giving the opportunity.
Of course, ma'am.
Okay. So Vishalatchi, you are taking the screenshot.
Yes, ma'am. I'm taking my screenshot. I hope everybody have shared the screen.
Mm.
Smile, please. Yes, ma'am. I had
So two, three screenshot you take by scrolling, because many participants are there. See,
Okay.
this is the 5th day, and so many days even speakers are not interacting like how Vishalakshi is interacting. So we
I
should
have learned a
be,
lot about, ma'am. Because of you, I have learned a lot from you only.
see, actually always we are giving opportunity to IASC and bigger. We should give opportunity to the person who can teach you and you will learn. That is also important. So I have balance with in my speakers, 15 days speakers. I have balanced both the side. I have
Thank you.
given
Thank you so much.
some few senior position people, and
Yes, ma'am.
these people are also there, so that everybody will get opportunity and the forum to perform well.
Yes, ma'am.
Thank you, participant. Thank you, and thank
Thank
you,
you all. Thank you so
Vishalakshi.
much. Thank you, Preeta ma'am. Thank you so much for the opportunity. Thank you once again. Bye.
Thank you, thank you,
Bye.
thank you. Bye.
Yes.
So afternoon session will be by 2 o'clock.